Hi, welcome back. In this lecture, I want to introduce the Line Profiler module. That is a tool that allows us to profile a code line by line. So this is very important and will give information on which line is important to do the work of the optimization. By the end of this lecture, we will be able to deploy the Line Profiler tool in our code to profile line by line and understand performance bottleneck. We will also be able to understand and analyze the line profile output and identify fine-grained computational bottlenecks. So what is Line Profiler? So Line Profiler is a Python module for profiling line by line. It works by profiling individual function on a line-by-line basis. Remember, whenever we want to do profiling, we might use a different tool. We typically start with the C profile that I explained in the previous lecture to get a high-level view and guide which function to profile with the line profiler. Once we identify the most important and the most computationally intensive and the function that takes most of the time, we want to profile those specific function line by line, understand better how to optimize that function. For doing that, we can use the line profile module. To install it, we use a pip install and line profiler. This comes basically with a tool called the can prof, and what we need to do is to take the code and add a decorator add profile to mark the chosen function, to instrument the chosen function. As I told you, the line profiler comes with a script called the can.prof that we're going to use in order to obtain a statistical file with the profiling information. So this can.prof gives us the CPU time and other statistics for each line of the chosen function are recorded. So the first step, we need to go to our code. We identified the function that takes most of the time, the function that we think that we need to optimize, is to decide to tell line prof that we want to profile that particular function is as simple as it is. This is the function that we want to profile because we know that is the function that takes most of the time from our C profile information. So we just tell line profile by adding the decorator at profile before the function that you want to do. So it's as simple as that. We just add this at profile. Once we have our code with this extra line just before the function we want to profile, we can call Python -m and can.prof. That is the script that we're going to use to obtain profiling information. And then we -l and juliaset.py. What it does is basically instrumenting the code with the profiling information, running it, and producing a file that is called juliaset.lprof. So this lprof file is the file storing all the profiling information. One thing I want to make you notice is that the function now that has been profiled takes 54 seconds. If you remember from previous run, this typically takes on this laptop typically 5 seconds when it is instrumented. So the point I want to make on this slide is that this kind of very high heavy profiling comes with a overhead, so sunk cost, or roughly in this case of 10 times, right? So we cannot really run this in production because it will result in extremely high execution time, right? But we'll see in the next slide that the information that we get is very, very precious. So just to summarize this slide, we can use line profile. The first step is to obtain a file with the profile information that has extension lprof. To do that, we do Python -m can.prof, that is the name of the script that we want to run, -l and then the name of the code that we have instrumented with the @profile decorator. Now that we run the kernel-prof and we obtain the information about the profiling, what we need to do, we need to have a mean to output the results of our profiling. For doing that, we do Python -m line profiler. So in this case, we use the line profiler module, and then we just put the name of the output with the statistics about our performance measurement. When we do that, we got the output that is printed to the standard output, the screen. And that's you see, is organizing the line of the number of the lines of the code, how many hits when you do sampling is spent on this function, the time, the percentage that is being spent, and the line context, so we can understand where is the time spent line by line. By far, the most important column that we look at the profile information is the percentage of time that tells us where the time is spent by percentage line by line. So we can see that 36% of the time has been spent on this line here. So one of the things we don't know if the time is spent here in calculating this absolute function of the complex number z, or in this calculating on this statement. If we want to have more information about this, we need to split it up, this while into parts. So then we can have information line by line. But at this point, we don't know if it's here or here. It's likely here because we know that absolute function is a kind of called many times from the C profile information. Inside the loop, we see that the function that we calculate is quite expensive, 30%. One big surprise by analyzing this output file is that the incremental function n equal to n plus 1, it takes 28% of the time. So that's quite kind of interesting that n plus equal 1 is expensive, and this is due to the Python's dynamic lookup machinery that is working at every loop. Even though we are using the same type, in this case integer, for each variable in each loop. So there is overhead coming from loop. So to summarize this slide, when analyzing this calculate z serial pure Python, we saw that basically 1/3 of the time of this function is spent on calculating this absolute function and this condition here. 1/3 is spent on calculating the function, and then 1/3 of the time just spent on incrementing this n integer. Of course, this line profile allow us to understand improvement opportunities where we need to go. So we start with the C profile, give a big overview or where we need to focus on which function. Then we use the line profile module, first the kernel-prof and then line profile, to output the profile information that will tell us what are the specific lines of the code that are critical for performance. In this case, the performance, we identify that this loop is really the culprit for all the bad performance. We can do a few things. We can work on optimizing the list for Z. We can optimize definitely this incremental by probably writing this function, this entire function in C, and then bridging it with the Python. So the point I want to make is that this is an important tool that allows us to understand where to go when optimizing specific code. So to summarize this lecture, there are two important points the line profiler modules allow us to profile individual function by using @profile decorator, and we do that on line-by-line basis. Second, the analysis of the profile information, the so-called .lsprof file, shows us the code lines with the potential to be optimized. This is the last slides. Talk to you soon.